Hey, this is Brock Lemires, and in this video, I'm going to introduce the first nonlinear device that we typically look at in electrical engineering, and that is the diode. So when we start talking about diodes, we always start by looking at the p-n junction. So in this video, I'm going to talk about the device physics of how a p-n junction works, and that will lead us into how the diode behaves. Okay, so the first question is, what is a diode? Well, a diode is an electronic device, and it is a semiconductor-based device, and it only allows current to flow in one direction. And I say in normal operation, which means forward biased, and we'll cover what that means. So this is the symbol for a diode right here. So you have an anode and a cathode, and you'll notice that since current flows in one direction, this is what we call polarized. Okay, so it actually has, it matters which side of the diode you plug in which way. Okay, so on normal operation, current flows from the anode to the cathode. Okay, a diode is a passive device. All right, so it is a load. It is like, kind of like a resistor where it doesn't provide energy to your circuit. It takes energy. And a diode comes in forms that look like this. So I have a diode right here. So this is a diode. Okay, and you can see it's just a kind of like, you can plug it in just like a resistor. And then these are different little packages on here. And then it comes with markings on it to show you which side is the anode and which side is the cathode. So the mark is always on the cathode. And that's a diode, okay? You probably have heard of a light emitting diode or an LED. And what that is a diode that gives off light. And so we use the same symbol, but we put these little arrows that show that light is coming off of it. And so it gives off light when it's on. Okay, so diodes are essentially everywhere. Here's an example of like a through-hole diode, and you can see that the way you tell which side is the anode and the cathode is the longer lead is the anode, so it flows from the longer to the shorter. Okay, so that's it. Now what we're going to do is we're going to first talk about the theory of operation of this in this video, and then we'll go into like how we actually build circuits with it and analyze circuits. But what we're going to do now is just talk about the device physics. Okay, so a diode is based on what we call a p-n junction, okay? And we're going to look at the device physics of this, but it's not going to be heavy-duty math or anything like this. It's just kind of a conceptual understanding of what's going on. So let's begin. A p-type material, okay? We're going to build a material out of a semiconductor, substrate that has the characteristic that it has a positive charge. So we start with what we call intrinsic silicon as an example. So we'll just use silicon because it's, one of the most common. And when I say intrinsic, what I mean is that it's pure silicon. So what they do is they build these silicon wafers they grow them, they're like a crystal. And silicon, essentially they can remove all the impurities out of the silicon, and it will bond perfectly into this crystal. Now, silicon has a valence of 4. And what that means is that its outer orbital of electrons has 4. So it's happy when it's got 4 in there. Okay. And so it's perfect to bond with, like in a flat sheet of silicon, because it can basically bond with 4 neighbors just like this. So I show right here, like for example, this silicon right here, bond 1, bond 2, bond 3, bond 4. And so they can essentially share electrons in the outermost orbital, and that's how they bond. So it's a valence bond. Okay, so what we then do is once you grow that, then remember with semiconductors, you can change their behavior by doing multiple things. You can heat them up, cool them down, and that'll change their behavior. You can put a voltage across them, and that'll change their behavior. Or you can insert impurities. And so consider if we put in another material, okay, a small amount. Okay, we're not going to like make it half impurity, half silicon. It's like silicon is the majority of the material. But what would happen if we put in a material that had a valence of 3? And so let's take an example of boron. Okay, so it's got a valence of 3, and if you see its model here, it's happy when it's got 3 electrons in its outermost shell or outermost orbital. Well, what happens is that once you put it in there and you cool it down or you heat it up and all the bonds form, it basically will bond with silicon 1, 2, 3, and it's happy. So this boron is actually happy right now. The problem is the silicon atom right here is not so happy because it only has 1, 2, 3 bonds. And so it's got a bond that isn't connected to anything. And so it is essentially going, hey, I want an electron right here. Well, if it wants an electron to complete its valence, then it is attracting a positive charge. In effect, it is a hole. It wants an electron. So if there was an electron over here, it would get sucked into the silicon. And so what we've done there is we've essentially inserted a hole into the silicon lattice, or the silicon crystal, and that looks like a positive charge. And so what we have done is we have now created a material that has a positive charge carrier. And that means that we can use these holes to actually move charge across the silicon. So now when we come along and we draw what p-type material looks like, we typically draw it like this. You have a little block and you've got all these positive charge carriers in there. And that's all we really care about. We know that underneath the hood is silicon, right? So it's the majority of this is silicon, but we're trying to move these positive charge carriers around. We say that this p-type material has a majority charge carriers that are holes or positive. So we have a majority, the majority. However, this is semiconductor. Okay, this isn't an atom where we have like an anion or a cation where it's a single atom. This is made up of a whole bunch of atoms. Okay, a whole bunch of silicon, and so we also have minority charge carriers. And so within here, we could potentially use minority charge carriers to move current back and forth. And we would say that this silicon, this p-type material, has a minority charge carrier of electrons or negative. And now this is where we kind of move away from the words anion and cation. So if you remember, cation was the term that we used to describe like an atom that had a positive charge. So we removed an electron from it. But in this situation, we don't use those terms anymore. We call it p-type because we're talking about a semiconductor here. So this is a semiconductor material that has impurities in it, and it is now positively charged, but it has a positive majority charge carriers is what we say. So we stop using the term cation. Okay, so let's go and do the same thing with n-type materials. What we want to do is we want to build a material, a chunk of semiconductor that has a negative charge or a majority charge carriers of negative or electrons. So we start with silicon again. So we got our nice little silicon crystal here and valence of 4. And what we do is we then dope it with a material that has a valence of 5, such as arsenic. Okay, and so we take arsenic and we blast it in there, and it has a valence of 5, meaning that it wants 5 electrons in its outer orbital. Well, when you do this and you heat it all up, and then they form their perfect bonds, then what happens is that when you cool it down, arsenic says bond 1, bond 2, bond 3, bond 4, and it has an extra electron that it never found a bond with, a neighbor. And so this actually now has an excess electron that's just kind of floating right here. And we can use that electron to move current back and forth. So we say that this material now has a negative charge carrier. All right. And so when we draw the n-type material, we can say, okay, this n-type material has the majority charge carriers are electrons or negatives. And that's true. Okay. So this is the way we draw this. And of course, like I said, we know under the hood, it's silicon. This is a block of silicon, but we've put impurities in it to the point where we have a whole bunch of electrons that we can move around if we put a voltage across this. Again, it has minority charge carriers that can be used too. Okay, so it does have holes that exist within the lattice or the crystal, and they can be used. Okay, so whenever you talk about semiconductors, you'll see this reoccurring theme where you have majority charge carriers and minority charge carriers. And we might not use it that much when we look at diodes, but you always want to talk about it like that so that you can be set up for the next big thing. So again, we don't call this an anion, we call this an n-type material because it is a semiconductor. It's a bunch of material that's not just one atom. Okay, all right, so now we have our p-type material and our n-type material, and now you sit there and go, well, why don't we put these together and see what happens? So we put them together, and what happens is that when they touch, they become a junction. All right. Now you look at this, and one of the things that you immediately might think is, man, isn't this how a battery looked? And a battery does have this concept of positive and negative, but a battery is an active source. So we had anion, cation materials, and then an electrolyte, and it worked a lot different. But it is the same in that when we have this p-type and n-type material, current can only flow one way. What we're trying to do is we're trying to take these electrons and move them to the left, and then correspondingly the holes will move to the right. So this structure, this p-n structure, is inherently dictating that the current flows, the electrons flow this way, right to left, and then the current will flow left to right. Okay, so when we touch them together, they become a junction. Okay, so that's where this whole term p-n junction comes from. And over here on the p-type, we have holes, which are the plus signs, and then we have minority charge carriers, which are these little guys sprinkled in there, which are electrons. And then over here we have the negative charge, which are free electrons, and that's majority charge carriers. And then of course we have the little holes that are sprinkled in there, which are the positive. Okay, when you put these together, an interesting thing happens, okay? First and foremost, you will actually have the electrons attracted over into the hole side across the junction, and you will get a diffusion that happens, okay? So you just take these materials, touch them together. Luckily, they're both based on silicon, so they will bond to each other mechanically, and they will form an electron hole pair, or said another way, the negative charge will be attracted to the positive charge right at this boundary. And what happens is once it jumps into those holes right at this boundary, it actually creates a neutral charge, and this little region right here starts becoming depleted of charge. And what that means is that the electron hole pairs have canceled each other out, and you have neutral charge right here. So it's like, this is pretty sweet. Immediately I had this depletion region form right at the junction. But it's not done yet, right? So then what happens is that the positive and the negative charge still attract each other. It's just that this depletion region has created now kind of this edge or this boundary where they don't move any further because they'll eventually get to equilibrium. So you can kind of think of it as, so the negative moves to the left because it's attracted to this positive, and the positive moves to the right because it's attracted to this negative. But then your negative over here is back attracted to these positives, and these positives are attracted to these negatives. So you got like this kind of left pulling thing and right pulling thing, and they will eventually form an equilibrium and stop being attracted. Okay, and this all occurs within this depletion region. Okay, so it's this really fascinating thing that happens, and all you do is just make these materials and stick them together. Okay, now it will reach an equilibrium, but the trick is it actually creates a thing right here called the barrier potential. Now, potential really is potential. It really is, we're talking about electrical voltage. And why that's important is because this by itself, this little barrier potential, just due to the way that these negative charges and positive charges diffused and reached equilibrium, causes, or it prevents current from flowing when you put just a voltage across it. So it creates like this barrier. And so now the question becomes, well, how do you make current flow when you have this little barrier potential? Well, first of all, look, you're going to have to apply voltage to it, right? So we're going to have a voltage, and we're going to put positive and negative on it. Remember, in this structure where you have P and N, the current flow is going to be this way. It's going to go from P to N, which means it's anode to cathode. And really what it means is that the negative charge over here, these electrons are going to flow this way into the positive terminal of the voltage. So the electrons flow this way, and that's what dictates that this current can only go in one direction. Okay. All right. So now you have current flowing this way, and we need to touch the voltage to this p-n junction. Well, we're going to need some electrodes, okay? So this is now where we attach an electrode to this p-type semiconductor and an electrode to this n-type semiconductor, and this is where we name them, okay? So you have a cathode and you have an anode. Okay, so this terminal right here is called the cathode, and the cathode, remember, is where the current exits the device. So in this device, it's a passive device, so current is flowing this way, so that's why the current is coming out of the cathode. Remember, in a battery, the cathode actually was on the other side, so it's where the current, it was the positive side where the cathode was attached, but it just has to do with, cathode is the term that describes the terminal where current is coming out of. So in a passive device, the cathode is over here, and if it was an active device, it would be on the positive side. But anyway, that's just a kind of a side note. Okay, so now we have a way to connect the terminals to the actual p-n junction, and let's take a look at what happens. Okay, so what I want to do is, when I do it this way, it's called forward biasing. Okay, so forward biasing is what I call the normal operation of a diode, and you can essentially think about, you put a positive and a negative voltage across this. When I connect it that way, though, the barrier potential, it becomes like a specification of the device. So we call it the forward voltage, and we say, you know what? For current to flow, we have to actually put enough power or enough voltage supply across this PN junction so that we can overcome the voltage, the barrier potential, which is what we call the voltage or the forward voltage. Okay, so now let's take a look at what happens when we start increasing the power supply. Okay, so we have to overcome that. So here we are, and we're going to start talking. So Vs is equal to 0, nothing's happening. You have this voltage, this forward voltage or the barrier potential, and all of a sudden you apply a voltage. Well, think about what's going on. You have a plus side right here, and you are able to create a stronger positive charge within the P device. So you're pushing these positive charges to the right from the anode. And you're also applying a negative charge over here on the cathode, and you're pushing these electrons to the left. And so you start actually squeezing the depletion region, and you're starting to reduce this barrier. And then what happens when you go further, the barrier will actually completely vanish, and you now are in a situation where this is the form of the PN junction where current can start to flow. Now, at the very instant that you've overcome the barrier potential, current is not flowing. Okay, but as you get a little bit higher, what will happen is that it can start flowing, and then everything starts moving. So what happens is that you can have these electrons will be pushed, or actually pulled, through the p-type material, and then will flow over there, and then the power supply gives a electron over here, and that's how you just keep this thing going and going. So here's another graphic that's much better that's kind of an animation that shows how this works. So notice that this is the depletion region, and as you apply a higher and higher voltage, it shrinks and shrinks and shrinks, and then current just starts hammering. It is interesting to note that current, a tiny bit of current is flowing as you shrink that depletion region, but once you shrink it and make it disappear, the current just starts hammering through this thing. And essentially this PN junction will look like a short circuit, okay? All right, so let's put it all together and wrap this up. Diodes are made of PN junctions. That's why we studied the PN junction. And we really study the PN junction so that you understand what the barrier potential is. They have leads called the anode and the cathode, and they're polarized so that it matters which way you plug it in. And the characteristic of that PN junction is that it has a forward bias in which, or when you run it in forward bias mode, current only flows in one direction from the anode to the cathode, but you have to apply a voltage to it that is enough to overcome the barrier potential. Okay, so now this is an IV curve roughly of what a diode looks like. So let's say that I put a voltage across this, and what happens is that current only flows one way, and this is voltage here and ID. So you're sitting there, current doesn't flow backwards, so it can't have a negative current, or you can't have a negative current, it's 0. And then all of a sudden you increase the voltage enough until it's like turns on, the barrier potential is shrunk, and it just shoots through the roof, okay? And when I say shoots through the roof, it starts looking like a short circuit. So until you get a voltage across this thing that is equal to the barrier potential or the forward voltage of the diode, it won't turn on. Okay, so what kind of voltage are we talking about? Diodes, you can make them out of silicon and germanium. Silicon diodes have a forward voltage spec of 0.7. So you have to get at least 0.7 over them until they turn on. And then you have to, and germaniums are about 0.3. LEDs are made out of germanium and some other materials. Those ones have a higher forward voltage. Those are like 1.7 to 4 volts. So it takes more to turn them on. One thing that's really of interest is that once it turns on, it looks like a short circuit. So it doesn't have any resistance. That means you can't develop any more voltage. So what happens is that the voltage goes up, and then once it turns on, the voltage is just clamped. So it'll actually stay at the forward voltage. And so it's a trick because you can't put more voltage on it in a circuit configuration like shown here. And in fact, you never see diodes by themselves, okay? You always have a resistor to both limit the current and also basically take the rest of the voltage from the power supply that is above and beyond the forward voltage. So you never see a diode by itself. Okay, now one more note before we end. You can run a diode in reverse bias mode, but that is beyond what we are covering in this video. This video is just an introduction to diodes where we start with forward biasing, meaning that current only flows in one direction from the anode to the cathode. All right, that is it. That is an introduction to the PN junction and the start of understanding how a diode behaves. All right, see ya.